So dilation changes a figure's size, but not its shape. Similar figures have the same size, but can have different shape. Scale factor is the ratio between sides, what you would multiply the sides of one figure by to get the second figure. When we talk about dilations, we're talking about something that is changing size, but it's not changing shape. Let me see if I can draw an example of one. If I have a square here, and I dilate that square, that means I'm either going to make it bigger than it is, or I'm going to make it smaller than it is. I'm either going to shrink it or expand it. Imagine, think about your eyes. When you go to the eye doctor, your pupil will expand when they dilate it. It gets bigger. All right, that's why you have to wear those glasses so that too much light doesn't come in. Because when it's dark in a room, like everybody's eyes right now, their pupil is dilated. It's open. Because when it opens, it lets more light in so you can see better. When there's a lot of light, if you go outside right now, your pupil will get real small. All right? Because it doesn't need as much light to see well. Well, that's what a dilate, and it's always gonna, your eyes are always gonna dilate proportionally. All right? Because you're dealing with a circle, your pupil's a circle, it's gonna always be proportional. Well, when it comes to dilation of a polygon, something like a square or triangle, when we dilate it, we're going to end up with a figure that's exactly the same size, exactly the same shape, just a different size. Okay, so they're not the same figure, they're not congruent, okay, but they look alike. They're just a different size. All right, and you can also do smaller ones. Think of a target. These circles. And this is not a good drawing, but those are called concentric circles. Okay, circles of around circles, and that looks like a target. All right, those are dilations. All right, similar figures have the same shape, but can have different size. They have the same shape, but can have different size. If they're the same size, they're also similar. So they can be different size or the same size. That's why it says, but can have different size. They have the same shape, but can have different size. All right, scale factor. This is the important thing about when we talk about dilations and similarity. That's the overall concept we're headed toward, is similarity. Scale factor is the most important thing about it. Okay? And if you were in Coach Rankin's class last year, you talked all about scale factor. You dealt with it a lot. This is the number that you multiply by to either get the bigger figure or the smaller figure. So you might be multiplying by a scale factor of 1/2. What would that do to all the features of, let's say, a square? If you multiply by a scale factor of 1/2, what does it do to the new figure? Is it going to be smaller or bigger? If you multiply by 1/2. If you take half of its dimensions, is you going to have a bigger figure, or are you going to end up with a bigger figure or a smaller figure? Smaller, because you're cutting everything in half. If I multiply, let's say I multiply this first square here, all of its dimensions are like the coordinates, the length of the sides. If I multiply all that by 2, am I going to end up with a bigger square or a smaller square? Bigger. All right? Because I'm doubling everything. Whereas a minute ago I said cut it in half, you're going to cut everything in half. You're getting smaller. So the scale factor is the ratio between sides. This is what you multiply the sides of one figure by to get the second figure. So, again, with my square, if the length of this side is 2, and I want to triple the size of this figure, I'm going to multiply the 2 by 3. So now the length of my sides would be 6. I just tripled each side length. It's not complicated. All right? Whoops. Okay, if the scale factor is greater than 1, it gets larger. All right. If the scale factor is 1, it stays the same. If the scale factor is between 0 and 1, in other words, like 1/2, it gets smaller. And we're not going to be dealing with any negative scale factors. Okay? All right. Now let's take a look at this little example here. We got figure 1 and figure 2. Figure 1 is the pre-image. Figure 2 is the image. How do I know that this is the original one right here? How do I know figure 1 is the original? Exactly. It doesn't have the little primes on there. All right, so I'm going to take a minute to graph this on the paper, on the board, and you can graph it on your paper as well. I can ask you different questions about this dilation. I can first say, all right, graph it. And so we saw how to graph it. We graphed both of these figures. And we saw that the second figure is 2 times the size of the first figure. The side lengths have been multiplied by 2. Basically, each dimension, each x and y value has been multiplied by 2. That causes the side lengths to be doubled as well. All right, we can do it that way, and I say graph it. But we can also ask the question, what is the scale factor? You don't need to graph it to be able to recognize the scale factor. I can just look at the figures. And if I'm multiplying each of the coordinates by 2, for example, then I know that that's the scale factor. But if I notice that I'm multiplying by 2 up here and by 4 down here, then this is not a dilation. Okay? So in this case, it is a dilation. Any questions about that? All right, let's take a look at another one. This is one where we don't necessarily have to graph it. It says, graph the following and tell if figures 2, 3, and 4 are dilations of figure 1. If so, give the scale factor. All right, we're not going to graph this right this second. But we are going to determine if these are dilations. All right? And if they are, we're going to give the scale factor. So let's look at 1 to 2, 1 to 3, 1 to 4. So let's look at 1 and 2. All right, 4 times 2 is 8. 2 times 2 is 4. 4 times 2 is 8. Negative 2 times 2 is negative 4. Negative 4 times 2 is negative 8. Negative 2 times 2 is negative 4. Negative 4 times 2 is negative 8. 2 times 2 is 4. Is everything good on that one? So between these two, it's times 2. So the answer is yes. And the scale factor is 2. All right. Now let's look at figures 1 and 3. I go from 4 to 2 and 2 to 1. They're both being divided by 2, right? Or multiplied by 1/2. All right, 4 to 2, negative 1, 2 to negative 1. That's consistent. Negative 4 to negative 2, negative 2 to negative 1. Again, yes, we're dividing it by 2. We're multiplying by 1/2. Negative 4 to negative 2, 2 to 1. Yes. So you can say times 1/2. We want to think of it as multiplication of a fraction instead of dividing by 2. I will give you credit if you said divided by 2. But you're taking the scale factor of 1/2. All right, so the answer is yes. All right, let's take a look at figures 1 and 4. 4 to 4, 2 to 4. Were we consistent? No. Do I need to look at any of the other ones? Nope. So from figure 1 to 4, the answer is no. It's not a dilation. And if it's not a dilation, there is not a scale factor. To have a dilation, they have to be consistent every time. What you multiply by has to be the same every time for them to be dilations. All right, let's move on. Okay, here we have another set of coordinates with 4 different figures. the first figure is drawn for us. Okay? And so now we're going to graph these other ones. So you can see that figure 4 is the only one that is not a dilation because the side lengths have not been scaled proportionally compared to the original figure 1. Okay, is figure 2 a dilation of figure 1? If so, what is the scale factor? So here it's not asking you to graph. Don't graph anything. Let's just look at it. So figure 2 is the bigger triangle. Figure 1 is inside. The question is figure 2 the scale factor? Is it a dilation of figure 1? And what is the scale factor? So what we have to do is look at the sides. So we got a bottom side here that is 8. We got a bottom side here that is 4. So on the first glance, does it appear that they are dilations of one another? Yes, it does appear that way. All right. It appears that the scale factor equals 2. That figure 2 is double the size of figure 1. Now, we would have to be a little more technical if we're going to prove this. In other words, to prove this, I would need to know that each side length is double figure 1. And I would do that by using what's called the distance formula. Now, I don't want to get into the distance formula right now, but y'all learned the distance formula last year, right? Y'all remember it? The distance d equals the square root of x minus x1 minus y1 squared plus x2 minus y2 squared. And you can plug all that in the calculator, it's no big deal. But that's the distance formula. In other words, I would need to know the coordinates of these endpoints and plug them into the formula to see if this length is double this length. But I'll go ahead and tell you, these are regular triangles, and a regular triangle is a triangle that all 3 sides are the same. Okay? So if that's the case, this is definitely a dilation. Alright, so we'll go ahead and say yes, scale factor 2. Alright, look at this one. Is figure 1 a dilation of figure 2? If so, what is the scale factor? So you got 2 triangles. You got triangle 1 and you got triangle 2. Alright, triangle 2 is the whole overall thing. He says yes. These are regular triangles. Alright, that means that all 3 sides are the same. So this side is 3. The bigger side is 3, 6, 9. So 3 times 3 is 9. So what's my scale factor? 3. Well, it's partially 3. It says is figure 1 a dilation of figure 2? So I'm getting smaller. If I'm going from 2 to 1, so what is my scale factor? 1/3. Thank you. Because it's 1/3 the size of the big one. So you got to be careful when it says is figure 1 a dilation of figure 2. That means it's going from 2 to 1. In the previous problem, we were going from 1 to 2 because it says is figure 2 a dilation of figure 1 from 1 to 2. So you just got to be careful in how it's worded. All right, now let me pause it here. Let's take a look at a video